Yesterday, what we were really doing was what I would call a type 1 problem. I'm going to break these up into types, and you'll see why when we get through all three of these. When I say type 1, what I mean is there's a simplification, something that makes the problem easier to do. For type 1 problems, we're talking about the situation where the object had just a horizontal velocity when it entered the air. So that when we set up our chart, so here's our little chart, vertical, horizontal, R, Vx, and T. And on this side I'm going to have delta Y, Vy initial, Vy final, A, and T. If you haven't really paid very close attention the last couple of days, then look at this just a minute. We are often finding the time, because the time is the thing that links these two. And we often have the initial conditions, things that happened at the start. We have the acceleration, we have how far it's going to go, we have the initial velocity, which often steers us to this relationship in order to find the time. If we're trying to be efficient, this will do it. Well, this is a quadratic. So we look for simplifications, things that will make the quadratic easier to solve. Anytime we can find a zero. So a type 1 problem places a zero here. The initial velocity is 0. That gets rid of this term. And because it gets rid of that term, it's a little bit easier to solve because I don't have to use the quadratic formula. Yes, sir?
Can you say that last part again?
The idea of a zero, or
like when you get rid of that little part.
Sure. When we have a problem like this, where the object is given an initial velocity that's all in the x direction, it doesn't have any vertical components, meaning it's not moving up or down at time 0. So I get to put a 0 here because it's not being launched at an angle. It has no initial vertical velocity, and that allows me to take away this term, which makes it easier to solve. That's the practice we did yesterday, and that worked out pretty well. So consider the one we're going to do today. The one we're going to do today, I think you can kind of guess where this is going to go. It's going to be a type. Can you guess? Oh, there it is. Yay! See, 2 problem. Wow, that's a real stretch. So type 2 problems, they're characterized a little bit differently. So when I call a type 2 problem, I call it type 2 is like this. Let me find something I need that. Yeah, straight line. Here we go. So a type 2 problem is like kicking a ball into the air. The ball is going to rise into the air and then come right back down to the ground. In a type 2 problem, although we introduce a bit of a complication, because we're going to introduce the idea of an angle and a launch velocity that's not purely vertical or horizontal, but both. That is complicated. But it also introduces another 0. Although the initial velocity will no longer be 0. There's going to be some initial vertical velocity because you've kicked it into the air. The displacement's 0. It comes back to the same level we were at. And because the displacement is 0, although this term comes back now, I'm going to have that term. This one becomes 0. So type 1 and type 2 problems have simplifications to make the math easier. It has nothing to do with physics. It's just a way to see if you understand projectiles without burdening you with all the math. Because, as you can probably expect, there's going to be a type of problem where the burden is going to change. Right? Let's look at a type 3 problem. In a type 3 problem, we don't have any simplifications. So consider a type 3 problem for a moment. Type 3 problem is going to have, say, a building, the same ball kicked at some angle, but now it's got a vertical velocity at the start. It lands some delta y before it hits the ground. You should notice that in this example, there's there's nothing I can make 0. The only way to kind of come at that problem is to recognize that you're going to have to be able to use the quadratic formula. And for a lot of you, that's a deal breaker. Not because you don't know how to do it. You all know how to do it. But look at all the steps it's going to take to get to this answer. Do you realize that this is just one piece of a long problem? So when I break these up into type 1, type 2, and type 3 problems, I'm trying to give you some kind of a framework to make sure you understand that the math can get in the way of the physics. And it can do so in such a way as I'm no longer testing the physics. I'm really testing the math. Projectile problems are complicated, but they're really complicated math problems. I want you to understand the nuance of the physics, and that's hard to do with all of this obscurity all around it. So let's focus for a moment. Let's do what I called a type 2 problem so that we can see kind of how this is going to play out when we start adding the angles into our questions. So in a type 2 problem, I already started to point out yesterday that a type 2 problem begins with an object being launched at an angle. That's where it begins. And because it's being launched at an angle, we have to kind of come to grips with how do you deal with the angle? What do we do that with that angle that's going to make this different? The first thing I want to point out is this is nothing more than polar notation, if you guys remember what that is. And if you don't, think of this as directions. This vector, even though it's a velocity vector, is still a vector. It's telling me to go from here to here. What I need are component vectors. Now, if you've never heard that word before, it's worth putting in your notes. It's a good vocabulary word to have. I'll be using the word component all year. A component vector is a set of right-angled vectors that replace a vector. Components are a set of right-angled vectors that replace a vector. Look, let's say you're here at the X, and you're trying to tell your friend how to get to this restaurant here. You can tell them to go that way, that far in that direction. That's what this vector is, that far in that direction. But if this is like downtown, there's probably a big building in the way. So instead, you tell them to go down First Avenue and make a left and go up 2nd Street. Right? Because they run at right angles to each other, but they get you around the building. Now, do you get to the same place?
Yes.
Sure. Component vectors are a set of right angle vectors that will replace our original vector. For us, these right angle vectors represent the vertical part of our velocity and the horizontal part of our velocity. Because for projectiles, only the vertical part is accelerated. The horizontal part is going to stay the same. We're going to be given a total velocity and an angle. We want to find out which part of it is acted on by gravity and which part isn't. That's the triangle part. Now, for all of you who practice the triangles, good stuff, glad you did it. Let's just run through it real fast. When we're dealing with trig and trying to figure out how these things are related, it all starts by knowing which angle is our focus. So you'll be told the angle to focus on for us. That's good because that means you'll know which side is the opposite and which side is the adjacent. That'll be given to you. And last, the diagonal is always the hypotenuse. With that being said, it should be pretty clear that sine of theta is going to be Vy initial over V. Right? Opposite over hypotenuse. Which means, if you're really paying attention, that Vy initial will always be V sine theta. Always. And at the same time, you can probably extrapolate this. Vx is always going to be V cosine theta. Always. If you're careful, You can see that through. So let's put this in perspective of a problem, how we would solve a problem. Let's get all that out of the way. I don't want you in there. Get out of the way. There we go. So, oops. All that into a problem. I kick a ball. Actually, let's hit a golf ball. 90 meters per second. Angle 30 degrees. Let me tell you, if you could really hit a ball at 90 meters per second, you would be like a golf god. Because this sucker is going to hit the ball like 1,000 meters. It's very unrealistic. But that's okay. For this problem, the numbers work out nice and sweet. So let's consider where the ball lands. I'm going to draw my same arrangement here. Starting with delta y, vy initial, vy final, a, and t.
Is that 30 degrees?
Yeah, 30 degrees, sorry. And on the horizontal side, range, Vx and t. Now, remember, when we have an angle given to us, when we have a launch velocity and angle, we're going to have to break it up into components. So you can just put this in your chart because it's always going to be v sine theta in the vertical direction. It's always going to be v cosine theta in the horizontal direction. Our angles are almost always going to be measured from the horizontal, so this will always be true. So when we start coming up with the information to put in here, and trying to place it where it's going to go, I think we know where to start. Delta y, 0. It's landing on the ground. Our initial y velocity, well, we're going to have to work it out. It's 90 sine 30 degrees. We're going to have to work it out. It's not hard. Sine of 30 is a half. So when you work that out, it's going to be 45 meters per second. Acceleration is still 10 meters per second squared. Gravity. And the last thing we know, well, the only other thing we know is the horizontal velocity. When we were given the velocity, we were given both. So this is going to be 90 cosine 30 degrees, which cosine is 0.866. So 90 times 0.866. I don't want to do that in my head.
79.8.
Thank you.
Or no, 77.9. I'm stupid.
77.9? No worries. All right. Do we have a framework? Sure. To solve it, we need to have been given 3 pieces on one side or 2 pieces on the other. It looks like we have our 3 pieces right here. Meaning I can figure out how long it's in the air. I can use that to figure out where it's going to land. Now, this is a motion problem. We've done this before. What you have here is the physics. It's a method to solve it that uses the physics you know to try and get us to an answer. Now, be careful. All of those things that we did in 1 dimension, we now have to do in 2. Choosing direction, applying it appropriately, picking a relationship, putting in our values, and finding a time. Yes, ma'am. To live up to my promise, though, I need to hurry, so I'm going to hurry, okay? My promise is on Fridays. I'd make sure you guys were able to be prepared. So look at this closely. Do not simply divide by t. Make sure you're careful here. I'm saying this because, not that I'm a math purist, but it'd be really easy to divide out by t. Make sure you're careful. You have to factor out the t. So this becomes negative 5t times t minus 9. I factored out negative 5t. That means that there's 2 times. There's t equals 0 is 1, and t equals 9 is the other. Now, it's important that you guys realize that the reason you get 2 times is because we asked math to tell us when the object was on the ground. So we get 2 answers because there are 2 times the object's on the ground. It's on the ground at 0, and it's on the ground at 9. I'm saying this because when you do the regular quadratic, you might get 2 times. And so you have to be careful about which time is the one to use. This one's easy. We don't want the 0. We want where it is after 9 seconds. But in other problems, it might not be so clear-cut. Yes, sir? Bye-bye.
One of the times is always going to be 0?
For these, yeah. When you're kicking off the ground, this one will always have a 0. That's going to be the initial time. But if it's the one we saw a minute ago with the building, you're going to have one time that's negative and one time that's positive.
Oh, yeah.
That's no big deal. You'll just pick the positive one. But what if you were to try and throw something to a friend on the roof? There's a time on the way up and a time on the way down. You have to choose the right one. Now, the rest of this is pretty straightforward, right, guys? Range is going to be 77.9 times 9, or 701 meters.